Welcome to another instructional video from OWL, the wise choice in fiber optic test equipment. I'm Professor Jim Powers. This video will demonstrate how to certify a single mode fiber optic link using a micro-OWL optical power meter and a laser OWL series single mode light source. There are 5 main steps in the process of certifying any fiber optic link. These steps are gathering link information and accessories, checking equipment and accessories for proper operation, entering link information into the certification tester if available, and setting an optical reference, also called zeroing, taking insertion loss measurements and storing test results, and then downloading stored test results to a PC and printing a certification test report. Before beginning any fiber test, the user must gather the necessary link information and accessories required to complete the test. Link information is used to help determine how much loss is acceptable for the fiber under test, otherwise known as a link budget. Optical loss measurements are compared to the link budget to determine if the fiber is good or not, which is the same as saying pass or fail. There are 5 key parameters that apply to any fiber optic test. First is the fiber type, which will be either single mode or multi-mode. In the case of multi-mode, this could be either 62.5 or 50 micron. Next is fiber length. It is important to know how much fiber is in the link under test in order to determine how much loss is acceptable for that particular length of fiber. Some OWL testers can be used to measure the end-to-end length of the fiber automatically, including the FiberOwl 4-bolt optical power meter. Otherwise, the user can use jacket markings, installation documents, or other length measurement methods such as OTDR. For best results, avoid estimating the fiber length whenever possible. Third is number of connections. A connection is the point where 2 fiber connectors mate together, such as in a patch panel, wall plate, or mating sleeve. Fourth is the number of splices, which can be either fusion or mechanical. For the purpose of calculating a link budget, most cabling standards do not distinguish between fusion and mechanical splices. Lastly, the user must determine what wavelengths they will test at. For multi-mode, this is 850 and/or 1300 nanometers, and for single mode, this is 1310 and/or 1550 nanometers. When using a micro-OWL or fiber-OWL optical power meter, these parameters can be entered directly into the device to calculate the link budget. However, if the link budget needs to be calculated manually, this is done simply by adding together the fiber loss, connection loss, and splice loss. Fiber loss is given in dB per kilometer and varies based on the fiber type and wavelength. To calculate fiber loss, multiply the fiber length in kilometers by the fiber loss. Connection loss is the number of connections multiplied by the dB loss per connection. Splice loss is the number of splices multiplied by the dB loss per splice. Most users will follow the fiber, connection, and splice loss specified in cabling standards, such as the TIA 568. It is also helpful to determine the connector type used in the link under test, which will help determine the right reference cable configuration to use. For accessories, it is highly recommended to keep at least 3 patch cables on hand, since there are 3 reference methods: 1 jumper, 2 jumper, and 3 jumper. Mating sleeves may also be required for some link configurations. Refer to OWL's video on reference methods for more information. Finally, if testing multi-mode fiber, the launch cable attached to the light source will also need to be wrapped around a mandrel according to cabling standards specifications. Refer to OWL's video on mandrels for more information. As you can see, we've gathered our equipment and accessories we will need for this test. So we're using the micro-OWL optical power meter, the laser OWL single mode light source, and 3 patch cables. Now, the reason we're using 3 patch cables is because we're demonstrating a dual wavelength measurement. So we need a patch cable for your 1310 port, your 1550 port for the light source side of the test, and you will also need a patch cable for the power meter side of the test. So what we're going to do first is we're going to check to make sure that these patch cables are okay to use for our measurement. So now we need to turn the units on. So we press the on button on the micro-OWL, the power button on the wave source, on the laser OWL, As you can see, the 1310 nanometer indicator LED is lit by default. So now we know that both units are powered on. We can connect in our first patch cable. And what we'll do is we'll just use the 1310 nanometer wavelength for this. It doesn't matter what wavelength we use. We're just going to make sure that they're not, or the patch cables are not bad. So once we connect in, as such, now we can start taking measurements here. Now for this purpose, for checking our equipment, the simple meter mode is the easiest to use. It's already highlighted here, so we're going to press F2 to select. And as you can see, we have a reading on the screen here. It's showing in dBm, that's what we want to see. However, we want to make sure that we're reading at the right wavelength. At this point, we're reading 850. So we need to change the wavelength on the power meter. This is simply done by pressing the F3 button. If you see wave here, it corresponds with the F3 button. So we press F3 until we read 1310 on the screen. Now, what we see on the screen here is minus 9.92. This is a very good patch cable. Our single mode light sources are NIST calibrated at minus 10 dBm, and that's our target value. We want to make sure that we're very close to minus 10. Now the reading might be a little higher, a little lower, as it is in this case, but as long as it's close, that patch cable is sufficient for use. So we know that this patch cable is good, and what we'll do is we'll check the other two patch cables. Now, as you can see, when I disconnected the cable, I'm getting a really low power level. What this means is that I'm just measuring room light. There's nothing to be alarmed about. This is normal. So we plug our second patch cable in. Okay. Now, as you can see, this patch cable is reading around minus 10.61. It's a little bit lower than our minus 10 value. And what we really want to do is make sure that our patch cable is not reading any lower than, say, minus 11 dBm. At that point, at that power level, it might be a good idea to replace the patch cable. But in this case, it's probably okay to use. So now that we know that this patch cable is good, we set it aside and we test our third patch cable. All right. Now, with this patch cable, we see that we're still reading very close to minus 10. So we know that this patch cable is also okay to use for our measurement. So once we've checked that our equipment and accessories are in proper operation, the next step is to set up the meter, enter the link information that we gathered earlier, and to zero out our equipment. Okay, now that we've made sure that our equipment and accessories are okay to use for this test, the next step is to enter the link information into the meter and to zero out the equipment. Now, if you remember from before, we were in simple meter. However, simple meter is not used for the certification process. So what we need to do is enter the certification area of the micro power meter. Now, for that, we have to go back to the operating mode screen. We simply press done to do that. As you can see at the operating mode screen, we have an option that says certify link. To move down to that option, we need to press F1, as I just did here, and then F2 to select. Now, at the start menu, you'll see two options here. Option number one is Link Wizard. Link Wizard is the process by which we're entering the link information that we will be using for the link under test. Now, to enter the Link Wizard information, we will not need the laser owl, so I'm going to set that aside temporarily here. We won't need any of the patch cables, so I'll set those aside as well. Okay, and I will zoom in on the screen here so you can see it a little better. Okay. Okay, now we're going to press number one for the Link Wizard. Now, Link Wizard is just going to ask us certain questions about the link that we're testing. and we're going to respond with the link information that we gathered earlier. So press 1 to start the link wizard. And now we'll see a screen that says select link. Now, as far as the micro-L is concerned, a link is simply a group of fibers that have identical characteristics. So the same fiber type, same fiber length, same connections, and same splices. Each one of these links, and there are 8 of them in the micro-L, each one of these links can store a separate set of configurations. So however many fibers you're using or testing, as long as they have the same characteristics, they can use this same link here. In this case, what we're going to do is we're just going to pick fiber link 1 for our test here. Once we pick the highlighted option, we press F2 to select. And here we're allowed to change the link name based on the job that you're doing or for the customer that you're testing for. I'm just going to leave it at the default value for now. Once we're done entering the link, though, we can simply press Done to continue. Then we're asked to put in the date of test. Now, obviously, it doesn't show today's date. This is a way to enter the date that will appear on the report, which is kind of nice. If you're testing tomorrow, but you're setting your equipment up today, you can put in tomorrow's date. But for what we're going to do today, we're just going to enter in today's date. Okay, now as you can see, our format is the 2-digit month, the 2-digit day, and 2-digit year. I've put in the date already, or I'm sorry, the month. But between all those digits, we need to put in some special characters. Special characters reside under the 0 key. So to enter a special character, you simply press and hold the 0 button. And for our purpose, a dash is okay to use. So we're going to enter in the date here, another separator, and then the year. Once we're done doing that, we press the Done key. The next screen we come up to is fiber standards. Now, fiber standards are simply a common set of rules that are used to test a fiber optic link. In this case, our default value is the TIA 568B.3. Okay, the B.3 is probably the most common standard used in the United States. In fact, if you're testing against the TIA 568C, you can use this option as well because the loss parameters did not change from one standard to the next. Now, as you can see, there are other standards there. Specifically, right below it is the ISO standard, which is used commonly in Europe. There are quite a few Ethernet standards you can choose, including 10 gig, as well as some user-definable standards for advanced users who want to configure their own TIA type link budget. But for our purpose, we're just going to pick the default value here. Once we have this value highlighted, we press F2 to select. And now we're asked to enter the fiber type of the link. Now we're doing a single mode test today. So what we'll do is we'll drop down to the indoor single mode option and then press F2 to select. And now we have to enter the length of the fiber link under test. Now, as you can see, it says feet here. Okay, there's a way to enter the length in either feet or meters by pressing the F2 button. And I'll press that a couple times. You can see what happens here. Okay, you can see that you can either enter in feet or meters. Now, most of the time, fiber lengths are given as feet on cable jacket markings, so we're going to enter the length in feet. And let's just say our length is 325 feet. So we enter the number 325, and we press Done to continue. The next question is asking us to enter the number of connections or patch panels in the link under test. Now, again, a connection is simply a patch panel, or it could be a wall plate or another mating sleeve, but really a point where two connectors come together. That air gap produced by those two connectors coming together is really what's being measured here. So, which is the same thing as what a patch panel does. So we're entering the number of patch panels. Now let's assume that we have a typical fiber link and we have one patch panel on either end of the fiber. So we're going to press the number 2 and then press Done. Now the last question that it's going to ask you is the number of splices in the link under test. Now most of the time you will not have splices in any link. Now, when it's asking this question as well, it could be either a fusion or a mechanical splice. Now, because this is single mode, odds are that you may have either fusion spliced a connector on, or you may have used a new connector style called a unicam or a no polish, no epoxy type connector, both of which are actually a splice. So if you have that sort of termination method on both sides of the link, you simply press the number 2 here. And let's assume that we did that. We press the number 2 and then we press done. Finally, we come up to a screen that shows us a review of the information that we're entering. So our TIA standard, 100 meters. The fiber standards need you to enter the length in meters or in the metric system. So the microAL converts it back to meters. 2 connections, 2 splices, indoor single mode fiber, and asking if this is correct. Now, if it's not, you simply press F3 to start over. But if it is correct, you simply press F1. Okay, now you can see on this screen, this is where you're setting a reference, otherwise known as zeroing. You can see our 2 wavelengths that are available based on the cabling standard we're using, 1310 and 1550. And you can see over on the right-hand side here is our reference in dBm. Okay, remember our target value is around -10, but it can be no lower than -11. So what we want to do is we want to set a reference for both wavelengths. Okay, this is where the laser owl comes back into place. So I'm going to zoom back out a little bit so we can see both units. Okay, now remembering that we're testing both wavelengths, 1310 and 1550 today, we're going to plug in a reference cable to both ports. So here's our 1310 reference cable and a 1550 reference cable. All right, now we've got those connected. Usually what we want to do is just start at 1310 to start. So we have to make sure that this little asterisk is in front of the 1310 nanometer. So we press F1 to do that. We're changing the wavelength. Okay, now that we're set to 1310 on this side, we're set to 1310 on this side. Now we can begin the set reference procedure by pressing F2. Okay, now we're prompted to connect our 1310 nanometer source. So we find our 1310 nanometer reference cable here, and we plug it in to the detector port on the microAL. Okay, once we've done that, we can confirm by pressing F1. And now the meter is just going to remind us that we're setting a 1310 reference, just to double check, just to make sure we didn't accidentally plug in the 1550. Then we press F1 to confirm. And it saves the reference. As you can see, it says -10.14. That's a very good reference here. So we've zeroed out at 1310, but now we need to zero out at 1550. So let's attach our 1550 patch cable and then change our wavelengths on both sides. So F1 on the microAL, the wavelength button here on the laser owl. As you can see, the light source switched wavelength, so you can see the 1550 LED is lit now. And we can press F2 again to set for 1550. And we connect our source and confirm that we've connected. Saves the reference and says -10.63. Remember, we're still approaching -11, but it's still not a bad cable to use. In fact, in the case like this where we're zeroing out the light source, we're also zeroing out any imperfections in the cable. So a reference level of -10.63 is okay. So now we've set our reference for both wavelengths. We're done with that part of the procedure. You simply press done, the done key here, or F3 for done to continue on. The meter will ask us if we want to begin taking readings for fiber link 1, which is our link name, and we do want to do that. And by doing so, we will come up to a screen where it shows us our readings. Now, what we want to do here is to take this opportunity to check to make sure that our equipment really is zeroed out. So let's make sure that that our readings should say 0.00. That's what we mean by zeroing. We have to make sure that, again, we're on the same wavelength, which we're not. See, 1310 here, 1550 here. So let's press the wave button on the micro owl. Okay, we can see we're very close to zero. So what this means is that we have confirmed that we've zeroed out at 1550. And let's do the same thing for 1310. So we take our 1310 reference cable and plug it in to the micro owl. And then we change our wavelengths on both sides. Okay, now you can see we're still very close to zero. What we've done is confirmed that we have zeroed out at both wavelengths that we're using for the test. Now, what I'd like to do is take the opportunity to explain a little bit about what's on the screen here on the micro owl screen. This big number here is your loss reading, and its loss is given in dB. So you want to make sure that you see dB over here. You have a pass rating, which means that you're passing against the standard. This little number over here is your overhead, and I will argue that overhead is just as important, if not more important, than loss, because this number tells you how close you are to passing or failing. The next line down shows us our fiber link name, or the job name, and as you can see here, it says new name. This is actually the fiber ID. Right now it says new name because we haven't stored any data yet. And then over on the right here, we see our currently set wavelength and our function keys at the bottom here. So now that we have checked our equipment, we've zeroed it out, it's time to start taking measurements. Okay, once we've set our link information and zeroed out our equipment, now it's time to take measurements on the link under test. So in order to do so, you take the laser owl with its reference cables to one side of the link, and you take your micro owl with its patch cable to the other side of the link. Now, one key thing to remember here, once you've set a reference, is to never disconnect these connectors from the light source port. By doing so, you run the risk of changing your reference level, and if you do so, then you'll have to re-zero and start over testing, right from the beginning. So it's better to never disconnect these connectors. So now we have our testers at the opposite ends of the link. We're going to connect into the link under test. What I've done here is I have a simulated fiber link. What this does is basically demonstrates that there is a patch panel on one side of the link and then a patch panel on the other side of the link. Okay, there's actually a coil of fiber in here that's simulating the fiber under test. Now, the first thing we need to do is we need to obviously connect into the first fiber that we're testing. So we get rid of the dust caps for fiber number 1. And what we're going to do is we're going to plug in our 1310 nanometer wavelength first. I'm sorry, into port number 1 here. Okay, as you can see, we have a reading here, -1.2, -1.3, somewhere in there. As you can see, it's passing. Okay, so this is a good reading. What we want to do once we have a pass reading is to store that reading into memory. Now, because this is the first reading that we're storing for this job, we want to enter the fiber label. Now, this fiber label is simply a prefix for a fiber number that the micro owl automatically appends. Now, that fiber number is based on the port number that you should be connecting into. So in this case, what we're going to do is we're going to leave it at the default value. This can be anything, but we'll leave it at the default value today. Once we're done entering, we'll press done. And you will see on the screen here, I don't know if you can see that. You see where it says fiber link 1. Okay, that's our job name. And we have our fiber ID, fiber:1. Shows us our indoor single mode fiber, our wavelength, our loss value, and our pass fail reading. Now we're satisfied with this result, so we're going to press F3 for save. Okay, now you can see on the screen here, it shows fiber number 2, which means that we need to plug in to the next fiber under test. Now, before I continue, I would like to explain a helpful tip about storing data for a dual wavelength measurement using specifically a laser owl light source. The easiest thing to do is to store all the readings at 1310 nanometer first, so all 6 readings here, and then change the wavelength only one time to 1550 and store the readings for that second wavelength. That way you don't have to keep disconnecting, reconnecting, and changing wavelengths, which actually opens up the possibility of getting your fiber readings out of sequence and things like that. Doing it one wavelength at a time is the best way to make sure that your data stays in sequence. So what we're going to do is we're going to store all 6 readings here for 1310, and I'm going to speed up the process here quickly. And finally, we'll store a reading for fiber number 6 here. Now, as you can see, we had pass readings for all of these fibers, so we're good at 1310 nanometers. As you can see, it says fiber number 7. It's prompting us to plug in the fiber number 7, which we don't have. At this point is when we switch our wavelengths. Okay, so we won't be using this 1310 nanometer reference cable anymore. We can disconnect it. We'll leave it connected to the light source for now. But we will plug in our 1550 nanometer cable to port number 1. Remember, we want to start over at the beginning. Okay, and again, we will plug in the port number 1 for the the micro owl. Now, as you can see, it says under here, obviously, because we are connected in to the wrong wavelength. So we need to press the wavelength button on both units. Okay, now you can see that we have a reading for 1550. But what I want to do is kind of point out that a nice feature about the micro owl is that the fiber number goes back to 1. So now what that means is that we can keep our 1310 and 1550 reading for each fiber together so that they appear together on the report. So we are plugged into fiber number 1 on our link under test at 1550 nanometers. We have a pass reading, as you can see here. So we're just going to store and then save. See, it says fiber number 1. So we have now we have a reading for fiber number 1 at both wavelengths. Now again, I'm going to speed up the process. Now you may notice that every time we disconnect and move to another fiber, you'll see that another reading shows up. Either it says under or some really low power level reading. Now that's normal because obviously we don't have a connection here. But once we plug in, we connect into the same fiber on both sides, you see that it goes back to showing you a power reading. We'll store our last reading here. Store, save. So what we've done is we've stored readings at both 1310 and 1550. They have all passed, so we're satisfied with the results. This is a good link. The next step in the process is to take the micro owl to a PC and download the test results to produce a certification report. Once data has been stored in the optical power meter, test results can be downloaded to a PC to produce the certification test report. First, install the USB driver and owl reporter software from the supplied CD or a USB flash drive. Connect the power meter to the PC using the supplied USB cable. and then power on the power meter. Then start the OWL Reporter program. The program shortcut can be found in the Start menu. When the software has started, the screen will initially say no data loaded as shown here. Download the test results to the PC by pressing either the download menu option or the download button. While downloading, the status bar will say searching for OWL device. Once the test results have successfully been downloaded, the data will appear in the OWL Reporter screen. The test results can be viewed in two different formats. This view is called Circuit Detail View. It shows detailed information about a single fiber run. The other view is called Circuit Summary View. Circuit Summary View shows basic information about a group of related fiber runs. Certain buttons become active when Summary View is selected. Pass-Fail, Overhead, which shows how close the test is to its fail point, or Optical Loss. Toggle between Summary and Detail View by pressing this arrow button. Test results can be printed from the File menu or Printer button. The printout will show test results based on the currently selected view. The reports are formatted to look like the OWL Reporter screen. This has been another instructional video from OWL, the wise choice in fiber optic test equipment. For more information about additional instructional videos, or OWL fiber optic test equipment in general, please visit OWL's website at owl-inc.com. I'm Professor Jim Powers. Thanks for watching.